Now, hood, the exhaust hood in a typical fire scenario is very, very important. So, based upon the fire size can be mentioned as the area of the burning surface or the heat release rate. See, for example, I can say some area, take a 1 meter diameter pan in which diesel is burning or petrol is burning, like that. Or I can mention a 10 megawatt fire, 100 megawatt fire, etc. So, when you create a fire, okay, FPA type of apparatus can accommodate larger fire powers. Fuel loading can be such that the fire power can be very high. So now let us take a typical example of FPA where we try to analyze a 10 megawatt fire. The compartment or the FPA facility should have a enclosure where the ceiling height should be 18.3 meters and the hood is kept over the fire. The hood diameter here, that should be 6.1 meters. This is the ASTM E2058 standard. There are similar European standards and so on. So, based upon the standards, we have to construct the hood. So, the hood is very big. The material of construction of the hood, piping, then the burning platform features, what you put to insulate that, then the weighing platform, everything comes from the standard document. Okay, so one more thing what we can do is the convective heat transported by the product gas can be estimated by a technique called gas temperature rise calorimetry, GTR calorimetry. The temperature difference between the exhaust and the incoming mixture or is measured and that GTR is determined. From the GTR we determine this and find the convective heat transported to the by the product gas. Okay, so typically there are several standard techniques which can be used to determine the flammability characteristics of materials, ignition characteristics, flame spread characteristics, mass burning characteristics, etc. Then flame spread rate. Then we can also measure the ignition heat flux, critical heat flux at which ignition can occur, ignition temperature, etc. And several parameters, combined parameters can be formulated. Then categorization of the materials occurs. Based upon the category, we use for several applications. Okay, now estimation of useful quantities. See, when you want to know what is the heat carried away by the fire gases, the mass flow rate of the product gases can be measured using orifice plate. Through the hood it goes and it goes through the orifice plate and we can find when the CD of the orifice is known, we can find the pressure drop across the orifice plate from which we know the flow rate. Then the product mixture, we know typically what it contains. So based upon that, we can have some properties of that, find the specific heat of that product mixture. We know the temperature also, we measure the temperature. So the specific heat of the mixture can be determined at the given temperature. Then we can find the convective heat release. That is the fire, how it loses the heat in a convective flow. Similarly, the net heat release can be measured because that is nothing but the mass burning rate into the calorific value of the fuel. Now the radiative, or we can also determine by using CDG, that is the carbon dioxide generation calorimetry or oxygen calorimetry. Then the radiative heat release will be difference between the net heat release and the convective heat release. Or we can also use radiation sensors and get the radiative heat release also. That is also possible, but costly techniques. Now, we have talked about smoke point. That is the minimum flow rate at which smoke is visibly seen from the fire. Okay, so that smoke point can also be measured from the calorimetries, whatever we have seen. Even cone convective can also give, because you can control your heat flux and burn it at whatever rate you want. Then find at what rate if it burns, smoke is visibly seen. Okay, then it can be calculated with several properties. Then combustion efficiency, that is, in a given scenario, how much complete combustion occurs, or CO, how much CO is generated, etc., can also be determined using the calorimetry. So that means these apparatus what we have discussed can give us several features and parameters which can be useful for us. Furthermore, we can also determine the corrosion hazards due to fire using these apparatus. Okay, based upon the release of certain chemicals, there may be some corrosion which can happen. That you can. Now, let us understand fire in a sense where we will talk about the lowest scale of fire to the largest scale of fire. That means the fire can be as small as a lab fire. That means you take a lab scale instrument and try to burn something there. Okay, or it can be a room heating fire. In a room, we typically put some wood logs in a particular place which is underneath a chimney and try to burn them so that the wood logs burn and radiatively you get the heat to the room. In cold countries they use this, and the smoke actually goes to the chimney out. So this is the smallest possible room heating fire. When I say fire, I will say some flame. I will see some flames in this. But we have also discussed about smoldering, where you will see that when you say charcoal, it is hot enough, oxygen comes to the surface, you see red hot surface. That is smoldering basically. So now we can also see such low level scales. So smoldering, so 10 power minus 3, it can be as small as 10 power minus 3 meter. Then come to candle flames, then waste bin, okay, then room. So you can see the typical scales, order of magnitude of the fire we are talking about in the dimension. Okay, now forest fires, it may be as long as 100 meters. It may be much more than that, but scale, I'm saying the order of magnitude. So the fire cannot be understood by conducting reduced scale or scaled down models. If I try to do some parameters and try to take the burning characteristic of a material in a given scale, say for example 10 power minus 1 meter, 0.1 meter scale, I try to do some experiments. When I do the experiment in 1 meter scale, you will see different characteristics. So basically what happens is, if you take, say, let us give a very simple example. You take a bowl of liquid fuel like kerosene or alcohol, say methanol. So the diameter is, say, some 25 mm, or 1 inch. Now you increase this, double this, and increase it again. Now it reaches, say, 8 centimeters, 50 centimeters, 1 meter diameter. Try to burn that. The characteristics will be entirely different in these scales. So the burning rate will increase, then asymptotically reaches a constant value. Flame height will actually increase, then again it will also reach a constant value. You will see transition to turbulence in particular scale of fire. So for example, if I increase the scale beyond, say, 15 centimeters, then I get transition to turbulence for the methanol pool. I'm just giving a typical example. Okay, now till 15 centimeter of pool diameter, you will mostly see laminar characteristics, but after 15 centimeter, transition occurs. Then after 25 centimeter, it will become fully turbulent. So whatever you see in the flow, initially flow can be laminar at low velocities for a given duct or any pipe, what you want to take. Then as the flow velocity increases, you will see that there is a transition, because you will see that Reynolds number has a critical value at which this transition occurs. Similar to that, here also the scaling of fires are very, very important because it actually determines the burning rate. But here, the scale down model cannot be used because, for example, if I increase the diameter more than say 25 centimeters or 50 centimeters, etc., then what happens is the burning rate per area will not change. So, how can you scale down that the burning rate when you try to do low scale experiment, say 1 centimeter to say 8 centimeter, you will see increasing burning rate as the diameter increases. But when you increase it from 25 centimeters to 100 centimeters, you will not see much variation. That means you cannot extrapolate this result to that scale. That is what is very important in fire. Cannot be easily understood. Fire behavior or fire hazard cannot be easily understood just by constructing a scale down model. So, what best we can do is try to understand certain parameters or non-dimensional numbers which arise from conservation equations of mass, momentum, energy and species and form some non-dimensional groups or non-dimensional numbers, what we can say. So, this will give you some parameters, or what we can do is we can best correlate the parameters what we have measured to these non-dimensional numbers. Okay, so let us see some non-dimensional numbers for the fire study. Okay, now for any non-dimensional group, we need a velocity scale, a length scale. Of course, the operating parameters or conditions like pressure and temperature should also be given to us. Okay, now with the velocity scale and the length scale, I can know what is the reference time scale for us. If, so let us say L is the length scale, U infinity is the velocity scale, then the reference time is L by U infinity. Now, in fire scenario, there is no forced convection generally. It is normally natural convection only. So, the velocity scale for most of the fire scenarios would arise due to buoyancy driven flow. Okay, so you may remember that for buoyancy driven flow, you use a number called Grashof number. Okay, so what it basically says is the velocity induced, the magnitude of the velocity which is induced due to natural convection will depend upon the length of the characteristic length of the scenario. See, for example, if I have a vertical plate of length L, so this vertical plate is hot, so its temperature is TH, and the ambient temperature is T infinity. So now what happens is there will be a flow which is induced due to the buoyancy because the particles, the air particles which are in contact with the hot plate will have a lower density, it will rise up and forms a pressure drop. So the cold air from the ambient comes in and there is a flow which is induced. So if you try to plot the velocity profile here for the, it will go like this. That means at the wall the velocity will be 0 and it also goes to 0 at the ambient side, and it actually produces a maximum value at a particular distance from the surface of the plate. But the average velocity which is induced can be determined by a term under root of GL, where G is the acceleration due to gravity. So G will be equal to 9.81. Okay, so under root GL, so G meter per second square into L meter, so meter square per second square, under root will be meter per second. So this product of GL under root as a unit of velocity, and this is the typical magnitude, not the exact magnitude, typical magnitude of flow induced during a buoyancy driven flow. So that velocity, average velocity, can be taken as u infinity. Please understand that these are all analysis which can be typically understood by, you can just put some anemometer and measure the velocity also at several places and take average. Okay, so when you do this, when you don't have forced convection, natural convection driven flow, this is a very simple technique by which you can estimate the buoyancy driven velocity. So under root of GL. Then you can find the reference time. So now let us go and see typical non-dimensional numbers which are used for our studies. First one is the Reynolds number. You might know this, ratio of inertial forces to the viscous force. Okay, inertia is the convection. Okay, so rho infinity u infinity L divided by viscous force. See, viscous force actually obstructs the flow. Okay, when the flow takes place past a solid surface, a boundary layer is formed. That is due to the viscous force. The flow sticks to the surface, so the velocity there is zero. And as you go away from the surface, you will see that the flow reaches the ambient condition, whatever be the force converting value, etc. So the flow actually takes place if there is no obstruction. The flow will have a given inertia, but if there is a viscous effect due to flow going past a solid surface, etc., then you will have some viscous effects. Okay, so the ratio of the inertial to viscous force is termed as Reynolds number. Very, very important parameter. As I told you, transition from laminar to turbulence is actually defined using critical Reynolds number. If there is a flat plate, flame tries to spread over this plate, that's a forced convection. Then whether the flame over the surface will be laminar or turbulent can be determined by calculating the Reynolds number based upon the length of the plate, the velocity of the air which is coming into this plate, over the plate, and the viscosity. Now please understand that we have to carefully calculate the value of rho and mu, because this is not a cold flow. It's not a cold solid over which a atmospheric air is flowing. It is a hot flow. That means there is a flame which is formed over the plate. Okay, so the flame will have gradient of temperature, will impose gradient of temperature. So you have to carefully choose the values of rho infinity mu, then calculate the Reynolds number based upon which you can categorize the flow as laminar or turbulent. Okay, now then another important number is called Froude number, which is nothing but the ratio of inertial force to the gravity force. See, for example, whether in a, see, take a burner, Bunsen burner. I supply fuel gas at a given flow rate so that the fuel comes out with a given velocity u infinity. Now the characteristics of the flame, because the diffusion flame, because the fuel alone comes out, reacts, the air from the ambient mixes with it, and wherever the mixing is close to stoichiometric proportions, the flame will be formed. Okay, so we'll see about this in the next module also. So now, if the characteristic of this flame is controlled by the convection or by the buoyancy, that can be determined by Froude number. Whether the flame formed is momentum controlled or inertia control or buoyancy control can be determined by the Froude number. Then Euler number. Euler number is nothing but the ratio of pressure force to the inertial force, P infinity by rho infinity u infinity square. So now this is very important because the denominator rho u infinity square is nothing but a dynamic pressure. So how the external pressure modulates the flow, that is given by the Euler number. Okay, rho u infinity square has a terms, the pressure units. Okay, it's called dynamic pressure. So Euler number is useful for understanding the convection part of the hot gases. For example, I told about the compartment fire, in which the flow goes out, hot gases goes out, and cold air comes in, etc., where you need to apply these concepts of dynamic pressure. Now, Prandtl number, there are three types of coefficients of diffusion. diffusion coefficient, what we can say. One is the mass diffusion coefficient, which is D, mass diffusivity we can say. Then momentum diffusion coefficient, then thermal diffusivity or thermal diffusion coefficient. So now taking the ratio of the momentum diffusion coefficient to the thermal diffusion coefficient or diffusivity, nu by alpha. See, nu and alpha both or any diffusion coefficient for the purpose as units of meters square per second. So now the momentum to thermal diffusivity will tell you about where the flame will be formed when there is a burning of horizontal layer, for example in a force convection, where the flame will be formed, where the boundary layer, hydrodynamic boundary layer will be formed, where the thermal boundary layer will be formed, etc. can be determined by this. You understand? See, for example, if Prandtl number is close to 1, then the boundary layer, hydrodynamic boundary layer and thermal boundary layer will be of same distance. Okay, so when Prandtl number values changes, then you will have differences in the thermal and hydrodynamic boundary layers. So normally you will have the flame which is formed below the hydrodynamic boundary layer. Then Biot number, when there is a solid, the solid has to be heated to release the pyrolysis gases. So now please see the solid has some geometric thickness, thermal conductivity, Cp, etc. Now when you have a heat flux incident on the solid surface, what happens is the based upon the thermal conductivity of the solid, thickness, etc., you will see that the temperature in the solid can be almost uniformly distributed. The Biot number basically gives the ratio of the conductive resistance to the convective resistance. So normally what happens, this is done when there is a solid interface, solid surface over which there is a hot flow or cold flow, whatever. It can be heat transfer in either direction. So now there is a heat transfer coefficient. Then there is a thickness of the solid. Then there is the thermal conductivity of the solid. H del W by Kw will specify the conductive to convective resistance. And if Biot number is less than 0.1, then the conductive resistance is almost negligible. That means whatever be the surface temperature, the internal temperature also will be almost close to that. That means I need not solve the conduction within the solid. Then another important number is called Nusselt number, which is the ratio of convective heat transfer to the conductive heat transfer. Please see the difference in the Biot number and the Nusselt number. Biot number talks about resistances. It says conductive resistance, heat resistance. See, what is resistance? Conductive resistance is nothing but, say, conduction depends upon K, gradient of temperature. So K into dt by dx. Okay. So now I can write dt by dx in integrated form, delta T by del. Del is the distance between these two temperatures. Delta T is the difference of the temperature itself. Now K into delta T by del. So del by K is the conductive resistance. Do you understand? So convective resistance is 1 by H. For example, area is common. So I am saying when there is a common area between these two. So the Biot number is defined in terms of resistances. And please see, one more important thing is the thermal conductivity of the solid has to be used, because this is more related to how the solid is going to be heated due to the convection. But Nusselt number says how fast the heat transfer occurs due to convection relative to conduction. That means we say that is surface. I don't worry about what is happening inside the surface. That is surface temperature. That is a fluid which is present. Basically, it is flowing. So it has a heat transfer coefficient and it has a thermal conductivity, fluid thermal conductivity. What is dominating? Convection is dominating or conduction is dominating? If H value is very low, then Nusselt number will be very low. Then conduction will be dominating the heat transfer and so on. So here you use the length scale, whatever you use for the fluid, and the Kf, the thermal conductivity of the fluid, is used here. Okay, so this is the important difference between the Nusselt number and the Biot number. Then we have several other features like non-dimensional numbers. Radiation energy divided by the convective thermal energy. Please understand that radiation, as I told you, in a scenario, in some instances, we will see that the convective heat transfer will be higher than the radiation. In some instances, we will see that the otherwise is important. See, for example, based upon the surface area of a solid fuel, convective heat transfer can be lesser dominant than the radiative heat transfer. So, how to find the relative uh, like a ratio, relative difference between these two? We define sigma T infinity cube divided by, this is nothing but, see, what is sigma T infinity power 4? That is the radiative heat flux. Okay, so there will be some epsilon also. Let us say it is black body radiation. So sigma T infinity power 4 divided by, if you take the denominator, it is rho, GL is velocity, C is specific heat. So rho multiply, so this is again some M into C. M, I will say M by area into C. Do you understand? So see, rho into A, area of cross section, into velocity will be the mass flow rate. When you divide by the area, you will get the flux. So rho into velocity will give you the mass flux, kg per meter square second, into C. That into T will give you the convective thermal energy. Do you understand? So radiative thermal energy divided by the convective thermal energy is a useful parameter for us, where you will determine the strength of the radiation and convection in a given scenario. Okay, now physical length to the radiation absorption length. Physical length is the characteristic length L. What is radiation absorption length? Radiation absorption length kappa has a unit of 1 by meter. That is, for a given distance, what is the amount of radiation it can absorb? Based upon, it is actually again a function of temperature, etc. Okay, so that is very important. Absorption coefficient or absorption length. So basically, this will help us to characterize whether the radiation is optically thin or optically thick. So this is also another radiative parameters. Then we have potential energy to enthalpy. Some features, see, for example, these non-dimensional numbers can be used for framing the correlations. So potential energy is nothing but G into mgh is the potential energy. So G into any length scale, that is the potential energy per unit mass, divided by enthalpy per unit mass is C into T. Correct? So that ratio is the potential energy to the enthalpy. Okay, now very important number called Zukowski number, which is the ratio of fire power to the enthalpy flow rate. What is fire power? Mass burning rate into delta Hc. One of the way to find it. Heat release rate. That's the fire power. Next, what is in the denominator? See this. Rho L square is like area. GL power 0.5 is velocity. So rho AV, what is that? Mass flow rate into C into T. That will be the enthalpy flow rate. Do you understand? So the ratio of the fire power, we are just trying to non-dimensionalize the fire power and use it for, so this will be equal to Q star, for example, non-dimensional fire power. This is actually called Zukowski number, which we can use to correlate several. For example, I can use this to correlate the flame length, burning rate, etc. So please understand that this is a very, very important number for us, where I non-dimensionalize the fire power using the enthalpy flow rate in a very simple form. Rho AV into C into T. That's it. Then another ratio of diffusion coefficients is called Schmidt number, where I have the ratio of momentum diffusion coefficient by the mass diffusivity. One thing to understand here, the mass diffusivity basically is a property of any two species in combination. So when I say oxygen nitrogen, I can write D of O2 to N2. This is a fundamental property between these two, which varies as a function of temperature and pressure. Okay, the rate at which oxygen can diffuse into nitrogen will be same as the rate at which nitrogen can diffuse into the oxygen, but it's dependent on temperature and pressure. Now, in the scenario where lot of species are present, then I have to calculate some coefficient, diffusion coefficient. Both have units of meter square per second, basically. So this we use some mixing rules. Or in a simple manner, what you can do is, normally when you use air, lot of nitrogen will be present. So product of combustion also will have tremendous amount of nitrogen. So I find the diffusion coefficient of a given species to the nitrogen. That will be enough for us to calculate this. Okay. So Schmidt number is another important ratio of the coefficient of momentum and mass diffusivity, which is also used for several correlations. Now, I have non-dimensionalized the fire power. Now, how to non-dimensionalize the mass burning rate of fuel? That is m dot fuel divided by rho a v, some mass flow rate of the gases. That's all. So, I am trying to specifically determine the ratio of the fuel flow rate divided by the product flow rate. That's all. So, that is another non-dimensional number I have. Okay, now coming to the solid again. What is the, so if you want to determine the time for ignition, etc., the rate at which a solid has to be heated should be known, because initially sensible heat is supplied to increase the temperature of the solid from a given temperature, ambient temperature, to ignition temperature. So transient conduction normal to the wall surface can be written in the non-dimensional form in this way: rho w Cw, thickness of the wall square, divided by thermal conductivity of the wall into reference time. As I told you, reference time can be calculated by L by U infinity. So this is another useful parameter. Then surface radiation to conduction is also another important this. See, relatively we have found the strength of convective to radiative heat transfer. Now in this case, what is, because the solid surface, the radiative heat loss can also occur. There is an incident heat flux. There is a radiation, re-radiation losses can also occur. Then the conductive loss also can occur to the thickness. So that ratio is the surface radiation to the conduction. So to quantify the heat loss basically from the solid. So these are the numbers typically used. I have given the nomenclature here for these numbers. For example, the reference time is TR, dynamic viscosity is mu Pascal second, then the reference density. As I told you, we need reference pressure, reference temperature, P infinity, T infinity. Then from that I can calculate the reference density, then specific heat, thermal conductivity of the solid wall, fluid, then the Stephen Boltzmann constant. Then absorption coefficient, as I told you, it has unit of 1 by meter. Then the heat release rate in watts. Then the heat of combustion specific to mass, joule per kg. Then the mass diffusivity or diffusion coefficient, meter square per second. Then the mass burning rate of fuel or the fire gas, that is kg per second. Then the wall thickness. So this finishes the module 1. Thank you.